we introduced a foliation of the spacetime. There, I think I said something was not quite correct. So let me just go back and make sure we're all on the same page. So imagine a foliation that we define a priori, let's say at least formally, and that foliation is labeled by this label T. Naturally, we can define a normal to any given hypersurface. That normal had to be time-like so that the surfaces are space-like. We're choosing that particular decomposition based on a series of space-like hypersurfaces. If we follow the normal onto the next hypersurface, wherever that normal meets the next hypersurface, we don't have to have the same labels here and there. And to adjust for that, we accounted for a shift vector. And the proper time between these 2 points doesn't have to be delta t. It's proportional to delta t, of course. And the proportionality function we call alpha. That's our lapse function. But that doesn't necessarily have to be the flow of, say, a congruence that we think gives us kind of a time evolution from one hypersurface to the next one. Let's imagine that's that curve with tangent ddt. Is the one we're going to use today to try and relate a rate of change of intrinsic metric and extrinsic curvature from one hypersurface to the next one. We proved the extrinsic curvature tensor was symmetric by at least locally thinking of another curve labeled by T prime, whose tangent was equal to NA. And that was the one we used to just show that the symmetry of that. What we want to do today is just write an evolution equation for the metric and the extrinsic curvature along these flow lines. So we derive this Hamiltonian momentum constraint using the Gauss-Codazzi and the Codazzi-Mainardi equations or relations, which involve either 4 projections onto the hypersurface or 3 projections and 1 projection onto the tangent to the vector n. The last one we had to include is this one where we had 2 and 2. So when we have 2 projections onto the hypersurface and 2 tangent to the vector n, then we have this relation. And now we're going to just manipulate our relation to try and obtain the evolution equation we want to get. So let's consider a few relations. So let's think of what we get if we construct the following contractions. So if I operate this way, so I'm going to use this in a second, but here I have 2 contractions, and I consider contracting the Riemann with n lambda and sigma and g lambda plus g sigma. If we combine, notice what this is. N lambda and sigma plus g lambda sigma is nothing but the projector. So this is the same.
What do you have in your first Riemann tensor? Just 5 indices, or?
1, 2, 3. Oh, sorry. But it's delta lambda kappa sigma. Should be the same also. Sorry about that. So this is the same as. So this part. So let me just write. We have now 3 projections, but these are both wind index up. I can now relate this one to the previous one. Let me just write this way. Then this piece gives me the standard. Notice that this gives me lambda and sigma, and contracting these two, this is R delta kappa. Now I can use Einstein's equations to rewrite R delta kappa in terms of and this comes from the definition of the Einstein tensor as R P minus 1 GP R, but this is equal to 8 pi TAB. So what we have to do is take this equation, take its trace, and replace R by a trace of T. So then either you can write the equation this way, or you can write it this way. So this is just a one-line exercise. You can rewrite Einstein's equations this way, which we use here. And then we can put things together and write the following. So notice, so here we have used a few things already. So we use that the lead derivative along n is the same thing. Well, we use n, the relationship between n, a, and d dt. And we also use the fact that this one is orthogonal to n to be able to pull the alpha, which then we send it to the right-hand side in here. That simplifies that alpha and gives you an overall factor of alpha in front. And we have yet to use this observation, because it's the projection of the Ricci's tensor onto the hypersurface, and we can choose to write that in terms of the stationary tensor. So I can rewrite this. Just do that this way. So here what we've done is replace, using Einstein's equations again, the Ricci by the source, which then allow us to link it to a stationary tensor if we have any. So if we are in vacuum, this is 0, and then the equation of motion for the extrinsic curvature is just given by that. If not, then we have the source. We have defined one extra tensor, this tensor SAB, which is just a projection of the stress energy tensor onto the hypersurface. So we bring this in front. Yeah. Let's work. So let us recapitulate where we are. So we introduce a decomposition of the space-time, and then we started projecting things onto things that are naturally on the hypersurface and are quantities that know how each hypersurface is embedded in the higher dimensional space and this vector n. And then we have this. We consider all possible projections of the Riemann tensor. There is nothing else we can do, because if we take an extra n and drop a projector, then we're going to have identically 0. We use Einstein's equations, and then we're able to write them in a different way. So we have 4 equations, this one equation, the Hamiltonian constraint, 3 equations for the momentum constraint, and the sources are here. Is this energy density measured by the observer whose tangent is n. This is the projection of the stress energy tensor on the hypersurface and one component on n. This gives us an energy, a notion of how energy is being transferred. And then we define this tensor, which is the projection of stress energy tensor onto the hypersurface. And altogether, we have 2 evolution equations, 2 constraints, so 2 set of constraints. See, 1 equation here and 3 vector equation here. This, we said, we mentioned a few things that neither lapse nor the shift show explicitly. And there is no second time derivative in this equation. And then we have 6 more equations here that tells us how the extrinsic curvature changes with time along this flow given by ddt. This equation has the lapse function shown explicitly. And in the right-hand side, we again see things that can be evaluated just on that hypersurface. So the initial value problem, if you want to think of what is it that we want to give at a given time to know what's going to happen in the future, is simply is that. So if someone comes and gives us gamma and the intrinsic metric to this hypersurface and the extrinsic metric to this hypersurface, we make a choice of lapse and shift. And we consider the sources if we're in non-vacuum space-time. This gives us a recipe to advance to the next hypersurface. Of course, the remaining one is a definition of K, the extrinsic curvature, in terms of the metric, right? Remember we introduced K as given by the Lie derivative of G and the shift. Let me just write it back for completeness. Let me put it here. So let's make a few more comments on this. So because of these constraints, these 12 quantities, if we're in 3+1 dimensions, are not free. There are 4 equations that constrain them. So this is very much akin to electrodynamics, where let me just write in the case of, in the absence of sources, we have the equation of motion for the electric field, the equation of motion for the magnetic field, and let's say we have the monopole constraint, and again, in the absence of sources, we have the divergence of the electric field being 0. We're not allowed to give E and B at any given initial time. Well, let me just define it this way. Think of it this way. This time, and and this space. And if we want to give E and B here at this initial hypersurface, our initial time, and use the evolution equations from Maxwell to advance to the future, these E and B are not completely free. They have to satisfy these equations. So they play the same role here. These are typically, depending on which literature you read, are known as the ADM equations, but they definitely are not the ADM equations. Put in between quotes. These are the ADM equations defined a la York, some people will call it. The original ADM equations were obtained in slightly different ways, coming from the action, introducing slightly different variables. There is a simple relation between them. The goal back then was completely different, was not to evolve the equations, but try and understand a possible path to a quantum theory of gravity. These equations were written more in a geometric dynamical point of view, where you wanted to regard the geometry as a dynamical entity and try to find the natural geometrical quantities to express the evolution of the spacetime. The relation between the true ADM equations and this one is just a simple change of variables, just given by this. So now this variable Pij is a canonical conjugate variable to gamma j. So this one does not have a simple geometrical interpretation as a kappa, the extrinsic curvature, but nevertheless they are related in a very simple way. So the equations of motions are almost the same. So if you rewrite the extrinsic curvature in terms of pi, and you replace in here, you derive an equation of motion for pi that way, and the equations of motions are almost the same, except that the ADM would want us to have another term. We want to have an equation that says dt of kappa ij, so from this equation, equal to exactly what we have, except for an extra term. So if we had instead started with those evolution equations and added this extra piece, which is I'm adding the Hamiltonian constraint up to a factor of 1/2, that's just a technicality, we would have obtained the same equations once we change k by pi, which leads us to the first set of comments we're going to make. So, of course, if you solve the equations this way or that way, a solution will be a solution regardless. It's just a relabeling of variables. But what is not true is that, using a slightly different terminology, off-shell, the equations would not be the same. So if you imagine that your initial data is such that slightly violates the constraints, this equation, with or without this term, does not give rise to the same solution. It's because we have a slightly different source. This would be the same as if I take this equation, say, for the sake of the argument, no one prevents me from saying I'm going to add here You would wonder, why do we do that? Well, we'll talk about this later. I think Will cover a particular example of that. I'll say a few other things. This equation will be with this term that I brought in from complete nowhere, but it may be useful in some instances. It's exactly the same analytical system that I had before because I'm adding a 0. But if we are to consider a slight perturbation of the initial configuration that may not satisfy dv equal to 0, now we have a different theory, and the solution to this equation can differ widely from the solution to this equation. So before I get or I say some more about that, let me just mention one last very important piece of information here, which is the following. Suppose you face yourself with the task of evolving or trying to obtain the future evolution of some given initial information on a given hypersurface. So let's take the first one, define or give data that, as we mentioned, the intrinsic curvature, the extrinsic curvature. You work hard to satisfy the constraints, and now you're going to evolve. And you're going to say, well, the evolution is sitting here in this equation, and of course in the definition of the relation between the rate of change of the intrinsic curvature and the extrinsic curvature. You evolve to the next hypersurface. You're sure that you're satisfying a subset of Einstein's equations, the subset that we use to write this equation. Are you satisfying the constraints? So that's the answer is yes, and let's see how we can understand that. So start with this. If we are satisfying, if we have a solution of Einstein's equations, of course we'll be satisfying that. And one thing we can do, and we have been doing all along, but now we're going to do it explicitly, is to take this equation and write it in terms of different components that we project parallel or orthogonal to the hypersurfaces. So this is the same as, let me just first write it, and then I'll give you the definitions. Where I define EAB to be gamma. So we just take our original equation, and if we project the Einstein equation with the right-hand side brought to the left so that we have a 0, that is equivalent to these three pieces that we are projecting the different components. If we project fully to the hypersurface, that's a component of this equation projected to the hypersurface. If we do a projection of 1 onto the hypersurface and the other one parallel to the vector n, we get this one. And if we do fully parallel to the vector n, then we get this one. So this is the Hamiltonian constraint, the momentum constraint, and the Einstein evolution equations. So that equation is nothing but this. So this tensor, if you want, which we want to know will stay 0 if we use the evolution equations, is exactly equivalent to that. So it's just, here is just a decomposition. This is, again, fully parallel to the hypersurface, 1 and 1, they are 1 and 1, and then the Hamiltonian constraint is orthogonal to the hypersurface. So now we want to know if I satisfies the momentum constraints and the Hamiltonian constraints at a given hypersurface, and I evolve with the evolution equations, will I stay satisfying the momentum and Hamiltonian constraint? And to see this, we're going to see it we're not going to go into all details, but we're going to give a pretty easy schematic argument for it. So first, we know, by virtue of Bianchi identities, that the divergence of G of the Einstein tensor have to be 0. And of course, the divergence of the Schrödinger tensor has to be 0. So the divergence of this has to be 0. So this is true. So now, when we take the divergence of this equation, of this expression, we get a 0. The divergence will contract one of the components, one of the free indices. We have an R free index, B. Let's contract that by B. So we take the divergence of these, and we want to know what happens with the result, the projection of it along the vector n. So now we're going to start playing around a little bit, because I can pull the n inside. So this expression, let me just write it here. So nb grad A of anything, let me just write that. FAB will be the same as grad A of FAB and B minus FAB grad A and B. When you're going to use this explicitly. Why? Because when we pull the n inside, the contraction of that thing with the n will let us recognize some of the components of the different equations in a simple manner. And of course, what we're picturing is that we initially satisfy the constraints, and we're going to evolve the future. So there are going to be pieces here that are constrained multiplied by the variation of n. But then these terms are 0 by definition, because we initially are satisfying. So let's just see where we go. So now let's pull this inside, and this will be equal to So what have I done? So I pull the n inside. When I pull the n inside, so n will be multiplying this. But remember what E was. E was the fully projected component of the Einstein equations onto the hypersurface. So n hitting E gives me 0. Now when n hits these terms, if n hits n, I have an m left over. But if n hits m, I have a 0, because m is projected onto the hypersurface. And then when n hits this one, okay, I have an overall contribution. So then we get no contributions from here. One contribution out of these two terms, this is in here. We have this one. And of course, we still have the, should I put a minus here? We have that piece, the piece from the Leibniz rules that we left out. So that's that contribution. So the next one, and of course in here, is present, right? So now let's take the next one. Let's contract with H. And again, we're going to get a very similar kind of argument. I pull H inside. When H hits E, I get something. When I hits one of these two, I get some R contribution. But when it gets there, it gives me 0. So this will give us So let me say a few more things. When we have to take the grad of HBC, H, we remember what it was. H was so grad of HBC is the same thing as grad acting on G, which gives us 0, plus grad acting on N, which gives us something. So again, gives us something like the extrinsic curvature and the acceleration perhaps, but it's multiplied by something that's supposed to be 0, but we have EAB here. That's the main point. So we can then see that this is something of this form. So again, very schematically, but let's see what we have. So we have something that is supposed to be 0. So I'm going to have a...
Is that gamma or H? Did you switch?
Which one? Here?
Oh, you switched the notation of the gammas on the H's.
Oh,
But
where did I do that? Many places. My bad. Did I do anywhere else? No. Yes. So from here, let's look at something else. From here, we would get a grad of n multiplied by h, and an n a grad a of h. So we have another equation that looks like n a grad a of h. So the structure is roughly like this. So we have the derivatives of m along the normal vector. See, this tells us how the momentum constraint and the Hamiltonian constraint change as we go, say, along the normal to the hypersurface. So this tells us how things are going to change if we give initial data on the given hypersurface that satisfies the constraint. Then we're asking the question, what will it take for them to continue being 0? This was 0 if we're satisfying the Bianchi identities. And from there, we see that that implies that the rate of change of m and h along that flow is given by things in the right-hand side. In the right-hand side, we have things that have, for instance, derivatives on that hypersurface of the constraints. But the constraints are satisfied on that hypersurface, so we get a satisfaction. But we also have things where E appears explicitly. And the only way we're going to satisfy it is if the evolution equations are being satisfied. So if we satisfy the evolution equations, then the right-hand side is 0. And therefore, these things are maintained 0 as an evolution. So the conclusion here is that if we give initial data satisfies the constraints at a given hypersurface, and we evolve that data with evolution equations, the constraints are going to remain satisfied.
what about the first term in the equation for the momentum constraint?
First term.
Yeah.
This one, you mean?
Yes, that one. That one.
Right. This is the one we have to impose. So that one will be satisfied.
Okay. All right.
This is satisfied by virtue of the initial data. Mm-hmm. But wherever we see the evolution, the good thing is that we don't see something like the derivative of this on the hypersurface, because it would have involved an extra derivative, like a third derivative in time. We don't have that. Everywhere that appears E is either a derivative on that hypersurface or the E itself.
Okay.
So that means we have to impose E, and then by that, we're implying now that the rate of change of M and H is 0. So after all this work, we have arrived to something that looks like what we wanted to have. We wanted to have something where we could make sense of the initial data, where not only do we have initial data that is complete, but it has a very nice geometrical meaning. It tells us what the curvature intrinsic to the hypersurface is and how that hypersurface is embedded. We have a full system of evolution equations. We have a sense of what type of initial data we can give that is consistent with our Einstein equations, and then we say that the evolution equations will take us to the future. And it also tells us that only a subset of the full equations need to be imposed. That's the EAB. And the other ones, the constraints will be automatically satisfied. So we have to do the hard work once. So I'm going to make a few comments now about what I just said. Not all what I said looks very nice. Unfortunately, the reality is far different from that. So what the picture I just told you is that we work to give initial data that satisfy these two sets of equations, the constraints, the momentum Hamiltonian constraint, and we evolve with that one. And if we do that, then these are automatically satisfied. In practical terms, that is usually referred to as free evolution. You do the evolution without caring what happens to the constraints because they will come for free, satisfied, if you had satisfied the initial hypersurface. That's just a choice. You could imagine trading in the iteration of some of these equations by the imposition of these as you evolve. So sometimes this is also referred to as partially constrained or fully constrained evolution, depending on how many of these you're imposing as you do the evolution. That's a bit technical. It depends on the particular application you're doing. But just in case you're interested or you see that terminology, that's what it refers to. We're going to just stay mainly on that camp where the term I refer to free evolution, where we think that we construct initial data that is consistent, and then we worry about the evolution equations and how the system is going to take. In that frame, we just said that the constraints are going to be satisfied and we're good, except that mathematics gets in the way. The equations of motion that we have written do not satisfy a key property of mathematics of PDEs. And that key property is called, is a concept that is larger than this, which is this one. So given any problem that we deal whatsoever in physics, Hadamard, in the early 900s, said the following conditions, that any problem that we're going to consider is physical will have to be well posed. And well posed means the problem that we're dealing with satisfies three conditions. So one is, of course, the existence of a solution. That's a given. We would find that totally natural to demand. The existence is the solution is unique. Again, that seems like trivial, but let me give you a particular example. Suppose we're trying to solve this problem. Well, let me just write it this way. So the wave equation for a scalar field in this box, and I decide to give initial data that is phi equal whatever, so some function. I give boundary conditions here, and I say that's my problem. So that problem is not well posed. Of course, the problem is myself, that is screwed up. I haven't defined completely the initial data that is required for this problem to have a solution. I also had to give the time derivatives of phi. So it's not only just the structure of the equation, it's the amount of data we're providing to guarantee that we have a solution, and that solution is unique. But the other one that is more delicate is the following. The solution depends continuously on the initial data. So I need to explain what that is. Let's go back to our example. So now I don't mess up. I give all the initial data that I need. I give dt phi, get phi. And with that, I get a solution. Let me call it U1 at some given time, let's say. Now I come and give another initial data that is kind of a small departure from the one I just used to obtain that solution. What this requirement states is that if I take epsilon going to 0, I get a whole family of solutions. And those solutions, as I take epsilon smaller and smaller, should approach that solution. So even chaotic systems satisfy that. Chaotic systems satisfy that. The problem is that the departure is wild. But if you take the initial configurations arbitrarily close to any one of them, the solutions will agree. If we don't satisfy this condition, then the problem is not said to be well posed, and we don't have control on the solution. Physically, we always know that when we're trying to describe a situation, we never give 100% with arbitrary accuracy the initial data that satisfies a given configuration. So we're always given something that is approximately close to what nature truly has. So this is the reason why Hadamard was thinking about this. If we are to, as a physicist, to try and understand nature, we will never have arbitrarily control on the initial configuration. Will be as good as we can get to, which will be quite approximately good, but never exactly. And if we don't have that, then how will we know that the solution we obtain has anything to do with the solution we are seeking? So in the context of PDEs, this translates into a whole bunch of conditions. And unfortunately, the equations we just written do not satisfy them. So I'll introduce some definitions that will, at the end, we want to have a kind of a particular recipe to try and understand or check if our problem is satisfying those conditions, and if they don't, where we have any freedom in trying to fix it to make sure it satisfies that. So in the example, we're talking about the difference between the true ADM equations and the ADM equations at La York. I mentioned that one difference is the Hamiltonian constraint shows up as another term. Or in the example of Maxwell's equations where I just shoved in BdV. It could be that with those terms, things behave differently. And it may be that with those terms, we actually can guarantee something like this. So we show precisely how we do that in one formulation of Einstein's equations, which actually makes a big difference. But let me try and explain what we mean. Let me give you first an example. So mathematically, what does this mean? Well, you can prove that if the following is true. Suppose, again, our solution U1, which is a solution to any problem at a given time, satisfies some bound of the form. This is for any reasonable norm. I'm going to give you first these. So if the norm of the solution with respect to the initial data grows, we're going to allow it to grow exponentially. We're going to allow it also to have an arbitrarily large factor in front. So if the norm of the solution at a given time can be bounded by the norm of its initial value with some possibly wildly departing function in front, as long as this beta and as long as this kappa or this k do not depend on the initial data, they are universal constants. So k and beta are universal. So independent on initial data and boundary data. If that's true, then you can prove that point through. So let me give you a very simple example as first, and then we're going to talk about the definitions. Let me construct the following problem. U, t. So we're going to have a problem with two unknowns. It's going to be first order in time, first order in space derivatives. So we have v, t equal v, x. we know exactly what the solution to this problem is. It's just an advection equation. But u is coupled to v by this term. So I'm going to rewrite this for sake of the algebraic procedure we're going to use later on to determine or try to assess if things are well behaved. Let me just think of the vector u now, which is u and v. So I can rewrite this problem as u comma t equal a matrix 1, 1, 0, 1 times u comma x. So let me just make an observation first. Notice this matrix is already in its Jordan form. Well, if you remember your algebra, the eigenvalues are obviously 1. But because there is a 1 there, the eigenvalues are degenerate. There is only one independent eigenvector behind describing this matrix. So that has profound consequences in the solution. So suppose you try to find the solution to this problem. And let's just try to find at least simple wave solutions where u, the vector u, x comma t, is written as an e to the I omega something times e to the st, e to the I omega So we do a Fourier decomposition in space, and then we try to understand what this equation tells us for this dependence in time. For this very simple problem, this is trivial. It's just simply e to the exponential of this matrix. So the solution is nothing but, it can be written in the following form, is the identity plus I omega 1, 1, 0, 1 times t times e to the I omega t plus x. So because of the presence of this 1, what we now have is something that has an exponential. So if I take the norm of this, we're going here. The norm of this gets rid of that part, because this has norm of 1. But we have now a linearly in time growth of the solution. Whereas yet, this linear in time growth has a dependence on the frequency of any given mode that I'm thinking about. Right? So think of the Fourier modes. Omega is a free parameter, so I can consider arbitrarily high frequencies. So initially, what I'm thinking is I can give data this way, or I can give data this way, right, with a lot of wiggles. And I don't care about the initial amplitude that's sitting here. I mean, this can be a very small amplitude, but very high frequency, and I'm going to have a higher growth. This translates in this equation that we cannot bound it. And by choosing higher and higher frequency on our initial data, the growth gets higher and higher. So this is potentially really bad, or it's already satisfying that, but you say, well, maybe a linear growth is not too bad, because it's growing, but not very, very widely. The problem is that if that was too simple a problem. Let's imagine that in addition to that, I add simply this. So the equation, I'm going to write it as v comma t equal v comma x plus u. So it seemed like I just added a very minor term. Well, if you now look for the solution, what you find out, and this can be solved explicitly, you have an exponential growth. Now you have an e to the, here you're going to have also e to the omega x, e to the omega t. So the linear growth gets turned into an exponential growth. And now we're in deep trouble, because it's not that the solution will slowly depart from, say, another solution that only differs in the initial data by a small amount, an arbitrary small amount in a high frequency, will be arbitrarily far when we go to a later time. So we're beginning to violate very strongly this third condition. So what we want is something to protect us. And the reason we want something to protect us as far as we care of PDEs is that look at how delicate this turned to be in the case of this very simple equation. We have a horrible mess in Einstein's equation, or in any of the kind of complicated PDEs that typically are used to describe physics. Who tells us that we're going to have simple problems like this, and then this happens to be very dependent on what we add. So you could think of playing and adding other terms, and now that growth gets worse in a significant way. So we care about a more robust system if we can understand it. And so we're going to introduce some definitions and some procedures or checks that we want to go through, at least to know how safe or not we are in treating a particular problem with a given PDE system. And this kind of, as a remark, stood in the way of numerical simulations of Einstein equations for a long time. And finally, many things came together, in particular understanding of topics like this, that allowed this situation to completely change. And I would argue in astrophysics, it is very common that people have found hacks to try to deal with problems that had we or everyone known better from the mathematics point of view, probably those hacks, we wouldn't be talking about those hacks today. They're very successful hacks. They're horrible. I don't like them. They work, but I think they're unnecessary given now the understanding that we have from the mathematics of the problem. And it turns out that indeed they were violating some of the conditions we're going to write now. So consider a Cauchy problem. Given by, I'm going to be general. So U is a vector that can have many unknowns. So it's a vector of all the unknowns. The unknowns we want to evolve from one time to the next one. This is a matrix. That's a derivative on the derivative of that U. So we're trying to write something in a very condensed form, but it's very, very general. We're also going to assume, so assume for now, A, the matrix is A, has constant coefficient. So A does not depend on time, space, or even the U itself. The beautiful thing is that we're going to come out with a set of conditions which are going to be so strong and so powerful, not so strong, so powerful in their implications that we can begin to remove things. We're going to be able to remove this assumption. Notice that here I'm not adding some term BU. This contains the derivatives of U, but I'm not adding an extra term that might have undifferentiated U values of the vector U. But we're also, once we look at the conditions that A was satisfied, we'd also let us remove that. So it's going to be as general at the end of the day to tell us, well, you can take that matrix. Matrix might be very complicated. Assume it has constant coefficients at any given point. Check these particular properties, and if those properties are satisfied, you can forget about that assumption, and the results will also apply if you have further terms in here that are undifferentiated with respect to U. So with that, now consider solutions. So consider solution of the form u of x and t, e to the I omega x. This is a vector going through all the dimensions of the space, given the space-time. So if we're thinking in 3 plus 1, this would be omega 1, 2, 3 times x, y, z times some u of omega t. And that's a function that will know what the time dependence will be of kind of plane waves that have frequency omega. If you replace this in here, then you have an equation of motion for u hat t. So this is, if we have a system of equations that is first order in time, first order in space, as far as the number of derivatives, if we look for solutions of plane waves, we're going to take arbitrarily high frequencies. Those are typically where things, the sensitivity shows up more clearly. You plug this into our original equation, then you can rewrite it this way. For simplicity, we took the norm of this vector omega. So now what we have in here is something where omega prime is within the unit circle. And then we're going to call this thing p omega, p of omega prime. So the conditions will be if the eigenvalues of p of omega are real, and please So the statement is the following. If we take this, which was the matrix we had before, remember in that very simple example, I have the metric 1, 1, 0, 1. When we pointed out, oh, look, there is a 1 off diagonal, that is potentially a problem. This is what this theorem is telling you. So if we go to p of omega prime, you check its eigenvalues. If they are all real, that's a necessary condition for a system to be well posed. Necessary in the sense that if it happens to be imaginary, one of our e to the I omega k plus t immediately becomes e to the omega t. So if they are not real, you should throw it away. So if anyone shows you an equation of motion for a PDE system in first order form that has, say, this form, then you should throw it away. Immediately, there is nothing else you have to do. This theorem tells you that's invariably going to lead to ill-posed problem. But that's not enough. In the example I gave you, we had the eigenvalues being real. They were equal to 1. The further condition is this one, that there has to be a complete set of linearly independent eigenvectors. And if that's true, the system is at least of type strongly hyperbolic. We're going to make a slight distinction of they're strongly symmetric, but for all intents and purposes, at the very least, this is where you want to be. If you satisfy that condition, then you can remove the constant coefficient problem. We can also consider other terms in the right-hand side, and well posing is satisfied. So this is a sufficient condition for a well-posed problem. provided you gave correct initial and boundary data. So this is for the first order in time, first order in space derivative problem. The equations we wrote, well, we wrote in first order in time, second order in space. I'm going to give you another definition for a problem that has second derivatives, which will be very similar to this. And at the end, we'll rely on this theorem again. But we're going to identify what the conditions are for these properties to be satisfied in the ADM equations, and we're going to see that the ADM equations fail that properly and discuss why. And with that, then we're going to give enough information for Will to then continue, and he'll show you how to go back to Einstein's equations, identify, or once we would have identified what the problem was, and deal with that. So we're going to stop here and do that tomorrow.